I'll also take this opportunity to thank Infosys Science Foundation because this general outreach activities of trying to, basically as scientists, I think we are happiest when we are doing our science. But, essentially, we're also members of society, so reaching out to other people to share with other people the excitement that we feel in the hope that other people will share at least some part of that excitement. That's a great enterprise. So I'll thank Infosys Foundation for that. And so now on with business. So I'll talk about hyperbolic geometry and chaos in the complex plane. Don't worry if you don't know these words or what they mean. So in Newton's time, there wasn't a distinction between mathematics and natural science. It's a limitation of our human brain that there has been this specialization and over specialization. Till today, I am a geometer, and if I speak to a number theorist and he's talking about some research in his area, after about half an hour, I will not be able to follow what he's talking about. So anyway, that's a limitation. We just have to live with it. But I think today the audience is largely natural science, and I happen to be a mathematician, so we'll have to start with a fairly uncontroversial definition of a natural object. This is a natural object, both according to mathematicians and according to people in natural science. Yeah. The problem with a mathematician's attitude towards this object is that it covers up its mathematical structure. So this foliage, which is crucial to the tree living, is completely irrelevant as far as the mathematician is concerned. So we strip it away. Okay. And once we strip it away, the geometric structure starts revealing itself. But even this is too much information for us to process. So we start simplifying this further and further till, as is the uncanny habit of mathematicians, it starts looking like anything but what we started off with. But that's okay. So next step, you start putting that on paper. So this is what a mathematician sometimes calls a tree. Okay. So yeah. So what is it? So you have, say, you have this point where it starts, and you have these three edges starting off from there, and then you look at any vertex on this picture. Every vertex has these three edges deviating from that. Yeah. So this is something we'll formally define what a tree is later on in mathematical terms. But so I'm roughly saying that this is really inspired by a real tree. Yeah? But even this, even as a picture, is a little complicated, so we simplify it still further. And now I think, we've pruned away a lot of stuff, but it still retains many of its essential features. And I'll just draw your attention to one thing, that as you proceed up, assume that this is the trunk, then you have these two branches, and then you have further branching, and then it goes up. All the branches become shorter and shorter. Yeah. I'll just draw your attention to this fact and then come back to it later on. Okay. Now, there's this non-uniformity, right? This edge here is much larger than this edge here. That's something that is a little abhorrent to us. So we make all edges equal. And finally, we have a mathematical notion of a tree. What is that? It's a collection of vertices joined by edges. The only thing is that there should not be any loops. So this is a mathematical example of a tree. So collection of vertices, these black blobs there, joined together by edges, and the only restriction is that if you want to go from one vertex to another vertex without retracing your path, then there's a unique path from any point to any other point. Okay, that's the definition of a tree as far as mathematics is concerned. Yeah. Just going back to the previous picture, these edges becoming shorter and shorter, that is not a failure of the artist. There's a mathematical fact behind it. If you try to draw a large tree inside flat Euclidean space, you are forced to make the peripheral edges shorter and shorter as you go further and further out. Okay, good. So this tree I'll tell you, I mean, I'll say it right away that a tree is a very naturally occurring example of hyperbolic geometry. Yeah. Going back to this previous picture, you see this kind of a tree, which I'll tell you what hyperbolic geometry is, but take it from me for the time being. That it's an example of hyperbolic geometry. But whenever you see such a thing inside Euclidean space, then it's forced to make the edges shorter and shorter as it goes off, and then you have something which is extremely wrinkled at the edge. So for those of you who know it, what it's going towards, if you repeat this process infinitely often, it's going to converge to the simplest fractal that we know, which is the Cantor set. So what is the Cantor set? You take the closed interval 0, 1, take all real numbers between 0 and 1, remove the middle 1/3. Now you have two intervals, 0 to 1/3, 2/3 to 1. Remove the middle 1/3 from there. Repeat infinitely often. What will you get? You will get the boundary of this tree, yeah, where the tree is converging towards. Yeah. So that is, so there were two terms in my title, hyperbolic geometry and fractals. Yeah. So the hyperbolic geometry comes here, and on the boundary there's a fractal. Okay. So that's roughly the motive that I want to communicate, and then we'll try to get at mathematical versions of this correspondence as we go further. Okay, so this is a tree. This kind of duality between hyperbolic geometry and fractals, it's not just, so what is a tree? A tree is, again, it's a locally it's a one-dimensional object, right? I mean, from any point to any other point, there's just one path. There's no planar object sitting inside there. Yeah. So it's a one-dimensional guy, and the boundary, as I told you, was this Cantor set, which was just a collection of points which are zero-dimensional, right? So what you should carry is that there's an n-dimensional object which has some geometry, which I'll detail later. I mean, I've given you an example of hyperbolic geometry in dimension 1. That's a tree converging to a fractal which is in one dimension less. But this dichotomy between n-dimensional hyperbolic geometry and fractal geometry in one dimension less is something that you see is ubiquitous in nature. Yeah, it's not something that's specific here. It just goes all over the place. I mean, it's you see it all over the place. So these are, well, sea anemones or anemones or sponges or something like that. They're sea creatures. So what's going on here? You have this round disc, yeah, and the fringe is this circle, right? It's this string which is tied into a closed loop, but it's extremely wavy. And that loop on the top, it bounds a disc, yeah? And that disc, if you look closely, say at a point here, this point here, actually it looks like a horse saddle, yeah? So there's some curvature which goes into the space and comes out, and then there's in an opposite direction, there's a bend, yeah? So a horse saddle looks bent in one direction if you see it from, say, the XY axis. If you look at it from the ZY axis, it bends the other way. Yeah? So a point where you have these two circles pointing in opposite directions, one upwards, one downwards, that's an example of a point where there's negative curvature. Yeah? So I'll tell you, I mean, what is the natural reason for this? It's actually fairly simple. I'll tell you why a little later. But you'll see that this kind of disk, it has lots of negative curvature points on it. Yeah, this negative curvature is also called hyperbolic geometry. So this is the two-dimensional version of hyperbolic geometry, is this occurrence of negative curvature. Lots and lots of saddle points. Yeah, and as soon as you have that occurring, when you look at the fringe, the boundary, that's a one-dimensional object, but that's extremely wavy. Yeah, that's an occurrence, a natural occurrence of a fractal, now in one dimension less. So it's a one dimension less than the geometry, than the dimension of the geometric space. So it's two-dimensional hyperbolic geometry versus one-dimensional fractal here. The previous example was one-dimensional hyperbolic geometry versus zero-dimensional fractal. Okay, let's go further. This is a three-dimensional hyperbolic geometry versus two-dimensional fractal. So the human brain, what happens is that the neurons, which is what constitutes the mass of the brain, they start dividing faster and faster, and therefore the surface becomes extremely wavy, extremely carunculated. Yeah? So this two-dimensional surface of the brain has something sort of resembling a fractal structure. The brain itself, if you look at its and I mean, if you model the brain in terms of, say, each neuron is is an edge of a graph, and you model the whole human brain, maybe what, 10 power 9 or 10 power 10 neurons of the order of that, then that will have a very, I mean, the geometry will be hyperbolic. Okay. So the next example that I have, it's just a coincidence that it just comes after the human brain. Okay, so the cauliflower also, I mean, this is a slice of this three-dimensional object, and I mean, that's like, yeah. So that's an example. You don't see slices of the human brain picture. So this is, I mean, as far as the geometry is concerned, there isn't very much difference. Okay, so this is also an example. I mean, if you put a cauliflower together, that's three-dimensional hyperbolic geometry inside, and there's a two-dimensional fractal on the boundary. Yeah. So yeah, get back to some pictures, but with a little more artistry, but still retaining enough mathematical structure. So this is an example of a tree, which is what we started off with. And then on the boundary, if you draw enough of these leaves, they start developing a fractal nature in one dimension less. Okay, good. So far, so good. And this abstract picture here, I won't explain to you what it means. I'll just tell you this much, that I'll come back to this picture at the end of my talk. Yeah? And what this picture says, I mean, there's a mathematical theorem lurking behind this picture. That blue stuff there, that's the complex plane. And think of this whole room where we are living as hyperbolic three-dimensional space. Yeah? So what's happening is that there's some geometric structure sitting inside this room, which is reflected in all those blobs that you see there. And if you look at the boundary, look at where it hits the complex plane, that's the boundary of that space, that's this extremely ornate object like an ornament, right? I mean, so that's got this fractal nature. So this stuff on the boundary has this fractal nature, and this inside, whatever the geometry is, that's three-dimensional hyperbolic geometry. I'll come back to the actual statement of what goes on behind this at the end. This is pinched from a book by three mathematicians, Mumford, Series, and Wright. It's called Indra's Pearls. Yeah, I think Mumford is an Indologist of sorts. He's a mathematician. I mean, he's worked both in pure mathematics and applied mathematics. He's worked on very abstract algebraic geometry. He's a Fields medalist. And then later on switched areas and started doing pattern recognition. So uses heavy-duty algebraic and differential geometry to recognize human faces from pictures. And he visits India very often. And so I think he picked up some mythological story. Why the book is called Indra's Pearls is the following. There's some infinitely reflecting sphere, yeah? And you have a chain of these guys arranged so that each pearl reflects all the other pearls within itself, yeah? And then the reflection goes on infinitely without losing intensity. Yeah, so therefore it's, it's got this name. And then once you have reflected infinitely many times, the collection of points that collection of reflections converges towards, that's a fractal. Yeah? So these Indra's pearls, what you do is you arrange a collection of spheres in, say, ordinary Euclidean space, make it into, say, some closed garland, assume that about each sphere, there's a reflection. What's outside gets reflected inside, what's inside gets reflected outside. Yeah? And therefore, you repeat this infinitely often. What do you converge towards? You converge to a fractal. Okay? So that's there behind this. I mean, and these are supposed to be the pearls. Okay? And this dust that you see on the complex plane at the end, that's the fractal. Okay, good. So now let's get to more formal stuff. I'll define for you what, I start giving some examples from natural science that I think I've stretched myself far beyond what I'm comfortable with. So let's define what a hyperbolic space is, yeah? So what is it? It's a space where, so I think you will not go far wrong for the purposes of this talk if you think of spaces either as spaces equipped with a metric, which means way of measuring things, as in relativity, or you think of them as graphs. Yeah? What are graphs? Graphs are just a collection of vertices and edges and you normalize so that each edge has length 1. Yeah. So once you have a graph, then given any two vertices, there is a shortest path between them. Okay? Sequence of edges such that the next edge, the initial point of the second edge is the terminal point of the first edge. That's an arbitrary path. Yeah? And since each edge has length 1, any edge path has a certain fixed length. Yeah? So then you can always talk about which is the shortest sequence of paths connecting one vertex to another vertex. Yeah? In Euclidean plane, in the plane that we live in, what is the shortest path connecting two points? That's what we call a straight line, right? So if you just abstract out that one property, that it is the shortest path between points, then, well, graphs certainly have that property. Two points can be joined by a shortest path. So that shortest path on the graph is the analog in the graph of a straight line. So a graph, think of it as a geometric object. Straight lines are replaced by these shortest path. Give them a name, call them geodesics. Okay? So what are geodesics? What are geodesics on this tree? So assume that you take this point here, the leftmost point and the rightmost point. The shortest path is the thing that comes to this root and then goes all the way up. Okay? All that you are not, what you are not allowed is what will not be the shortest is that you go to this vertex, come back and then go along. Why? Because then you can just remove this vertex, remove this edge and decrease the length of your path. Good. But now as soon as you have a notion of a straight line, you can have a notion of a triangle. What's a triangle? You take 3 points, say this point, and say this point in the middle. Yeah? As soon as you have 3 points, you can join them pairwise by shortest paths, analogs of straight lines. So what do? Say this is A, this is B, and this middle one is C. So AB is this path, AC is this goes down here and then comes up here, and then BC is it goes down here and comes up here. Correct? Throw away all the rest. What do you have? You have, and suppose you manage to straighten out this. So I'm just, yeah. Oh, there's a board here. Good. So so this is your A, this is your B, and you joined A to B by your shortest edge path, and from here you went up a few steps and you reach C. So if you extract this out from the picture, what does your triangle look like? A, B, and you have something C here. Forget all these vertices in the middle. So your edge is this is the edge AC, this is the edge BC, and this is the edge AB, right? So a triangle on a tree is just a tripod. Okay, so this is what it's called, a tripod. You can call it a tree, and typically you can call it a Y or a tree or a T. These are all three pictures of the same thing. So what's the crucial property of the triangle in a tree that is different from Euclidean space? Yeah. So look at that picture. I mean, this is that A, B, C is just this picture here, A, B, and C, and then you look at the tripod between them, and that's extracted out and drawn here. Yeah. Okay. So what's the property? It has a certain property which is very different from Euclidean triangles. You look at any edge here, say AB, that's actually contained in the union of these two edges. AC, union CB, the union of those two actually contains the third edge. Yeah? And that's really what motivated Gromov, one of these guys who put huge pieces of mathematics together. I mean, in this kind of a space, you can't possibly imagine doing anything like calculus, right? There's no differentiation or anything that you can possibly do, right? So, I mean, this is an extremely discrete space. In fact, actually, these edges are also there because of a certain psychological limitation. You can just look at, say, the distance between vertices and throw away all these edges, and that will still retain the geometry of the space. It's just a collection of points. So essentially, we call this broad scheme of things, broad way of looking at it, coarse geometry. Yeah, which means that if you want to do geometry but you have bad eyesight, yeah, you don't have resolution to see fine things, yeah, but you still want to do geometry. So what is it about space, yes? Yeah.
Then how is defining the metric? How will you define the metric?
Define the metric as follows. Define the distance between this point and this point as 1. This point and this point as 1. Just define the distance between. See, what is a metric? A metric is a way of saying distance between a pair of points is such and such.
But there is no structure if you remove the line edges.
What do you mean there's no structure? It's a map from this finite set cross itself to the positive real numbers. That's what it is. Formally, what is a metric? Formally, a metric is a map from a space X cross itself to the positive real numbers union 0, which satisfies a few properties, 3 properties. Distance of X comma Y is 0 if and only if X equals to Y. Property 1. 2. Distance between X and Y is equal to the distance between Y and X. Symmetry. Third, triangle inequality. Distance between X and Y, Y and Z, add them together, that's greater than or equal to distance between X and Z. You don't need a path for that. Now you abstract it. This is exactly what mathematicians do. I mean, you start off with something, then you throw away all that, then you write it down on paper. Now it's a function. And if, I mean, this is our snide thing, that if reality does not fit that model, well, so much the worse for reality. We'll work with this. Okay? Okay, so that's what. So the point is, I mean, what is the point of doing this abstraction? It's not for the sake of abstraction. Okay, the point is you sometimes all that structure is too much baggage to carry around, right? We want to get a map of a huge amount of the universe, but we have a very limited amount of space, right? So you'll have to throw out information, code it in stuff where only the important features are retained. Yeah? So that's why that's exactly what abstraction is about. Yeah? So here, if you look at just this abstract notion of a metric, then you can throw away all these edges. Yeah? You just have these points, and the distance between one point and another point is the distance that you would get if you imagined edges between them. Okay? And you imagine that this is the tree underlying it. Yeah? So even with that, basically what happens is that you don't get a map of the real line, you get a map of the positive integers. Yeah? So real line has become discretized. That's all. So this is just a discretization process. So, okay, so if you have a bunch of points, these are all zero-dimensional objects. Yeah? So you can't imagine any classical geometric tool, calculus, curvature, etc., to go through in this context. On the other hand, there are classical models of negative curvature, as I said. I mean, you have saddle points, so you have this horrible formula which we used to see in high school, d2y dx2 by 1 plus dy dx whole square whole to the power 3 by 2. That's some completely obscure formula. I mean, what does it mean? You take some curve in R2, take a point, just as a tangent line is your best linear approximant, you take the best circle approximant. This is a geometric way of understanding what curvature is about. Yeah? Take that path, take the best circle that fits that curve at that point. Take the radius of that circle, 1 by that radius is the curvature. That's it. Okay? Instead of linear fit, you take circle fit. That's it. So, but for that, that's where Newton is essential. Yeah? You have or Leibniz. I mean, you need calculus to do that. I mean, in order to calculate that, if you really want that value, then you need to do calculus. But in a finite collection of points, how are you going to fit circles? It doesn't make sense. So what Gromov did was he took all this stuff from this very discrete world of trees and groups, which I'll come to a little later, and the world of smooth manifolds or things which have these saddle points where you can do calculus, and extracted out the minimal structure that is necessary to put these two, the very discrete world and the very continuous world, smooth world, together in one framework. And this is the next definition. What is it that distinguishes a space with negative curvature? It is that triangles are thin. What does thin mean? So this edge AB, this bracket A comma B, denotes the edge from A to B. Yeah? And you have a space or a geodesic metric space, which means that any 2 points can be joined by a shortest path. Yeah? So that means straight lines exist in that space. These are the spaces that you're looking at. A metric space where you have geodesics is said to be hyperbolic if any side, if you take any triangle ABC, then AB is contained in the delta neighborhood of AC union BC. Okay? So here, in the previous example, the value of delta is actually 0. So what is happening? Now I'll draw one more picture. So you have A, you have B, you have C. I mean, triangles actually look thin in this sense. Yeah? What happens is that you take, depending on whether you're vegetarian or non-vegetarian, you can think of this as a banana or a sausage. Okay? So you take, this is the delta neighborhood of, this is the delta neighborhood of AC. Okay? This is AC. Now you look at the delta neighborhood of BC. This is delta. So you take AC, you fatten it up by delta. You take BC, you fatten it up by delta. AB lies in that, in the union of these two neighborhoods. Okay? So that's the notion of a space which is delta hyperbolic. Yeah? So that means that you look at a triangle, any triangle, that means union of three geodesics. Look at it from far. Yeah, somebody there at the back. Yeah.
Banana or sausage, whatever it is, be thinner. So
No.
AB is not.
Yeah. So the definition of the thing is the following, that delta thick banana, the union of two delta thick bananas contains the third side, means that the space is delta hyperbolic. That's part of the quantification. Okay? So I mean, you can have thinness at various scales, right? If you have thinness at scale delta, you say that the space is delta hyperbolic. Okay? Right? So delta could be 1, you could scale the space and it could become 1000. Alright? The point is that if some delta works for all triangles in the space, yeah, then you say that the space is delta hyperbolic. Okay? But what the actual value of delta is not important, because you can take some space and scale all distances by 100. Then what the delta that worked in your previous case, that's not going to work, but 100 times that is going to work. Right? You are interested in only large scale qualitative features because you can't do calculus. You have bad eyesight, so your resolution, see, basically this delta measures some kind of resolution, right? So these flies, yeah, I mean, okay, so I'm probably speaking to an audience which knows much more about eyes of flies than I do. But I mean, so eyes, they have bad focusing properties, right? So, but they'll see. But so if you see when a plane comes in, there are actually discrete lights on the path of a runway. But if you see it from far away, even say about when the plane just comes in, it looks like a straight line of lights, right? So that's what this is about. So imagine that you're looking at this geometry with bad eyesight, bad resolution. Yeah, where the resolution is delta. What that delta is, we don't care. It's a very democratic setup actually. I mean, people with very bad eyesight and slightly bad eyesight are not distinguished. Yeah. Go ahead.
If you just take the board as your space.
Yeah, the board is not, okay, I have come to that the board is not going to be an example of a space. So board meaning just this much? Yeah, so any finite object has a diameter, right? So take delta to be 1000 times the diameter of that board, then every triangle is going to fit into that, right? So that's not going to work. I mean, so then any finite space, yeah, any space whose diameter is bounded, yeah, has delta bounded by that diameter. So what you really are interested in is what happens in the very large scale, which means that all your spaces of interest are going to be of infinite expanse. Okay? So one example is, suppose you take flat Euclidean space. Okay? So this board is a piece of flat Euclidean plane. Is it delta hyperbolic for any delta? That's the question. Answer, no. You take an equilateral triangle. Yeah? That has delta at least equal to the in radius of that equilateral triangle. But you can keep scaling the equilateral triangle and you're still a triangle in your plane. So you give me a delta 1000. Yeah? I give you a triangle whose sides are all 50,000 in length. No side is going to be contained in the 1000 radius of the other two sides. You say, okay, this delta does not work. You give me some other delta. I'll tell you, give me any delta, I'll give you 1000 times the delta sized equilateral triangle, and that your delta will not work. So the Euclidean plane that we live in, yeah, it's actually an accident of nature that we live in a Euclidean plane. It's zero, right? I mean, zero is a measure zero choice in the collection of all real numbers. Generic geometries are actually hyperbolic in a certain very precise sense. So the Euclidean plane is not delta hyperbolic. Trees are. Yeah, it's a theorem of. I mean, so this the reason why these trees actually become shorter and shorter. The precise mathematical theory behind it is actually a theorem of Hilbert from 1900, which says that if you try to construct a complete negatively curved surface and fit it into three-dimensional Euclidean space, you will fail. Okay? So this failure is not, I mean, so what are those trees trying to do from a natural science point of view? What are those trees, these sea anemones, or the human brain, what are they trying to do? What they are trying to do is they are trying to develop maximum amount of surface area inside three-dimensional space. If you try to minimize surface area, you're going to get a sphere. If you try to maximize it, why? Because trees want sunlight. The human brain wants largest amount of interactions between neurons at the top. Huh? That whenever you try to maximize this area, surface area, you are going to develop these tendrils which go up. Yeah, that's an example of hyperbolic geometry. And a telltale signature of hyperbolic geometry is going to be when you see the surface of that, it's going to be a fractal. So anytime you see a fractal, and it's sitting on the surface, you just probe a little bit, you'll see that there's some hyperbolic geometry going on inside it. For a tree, the delta is 0. Because of this triangle. See, AB, the triangle edge, is contained in the 0 neighborhood of the union of AC and BC. If the ambient space is hyperbolic itself. So, for example, if you look at the space-time of relativity, x square plus y square plus z square minus t square equal to, that's your metric, yeah? And you look at the unit sphere in that metric, x square plus y square plus z square minus t square equal to minus 1. Or, if you change it around, plus 1, yeah? That sphere, and you look at the Lorentz metric and restrict it to the unit sphere, that is the standard three-dimensional hyperbolic space which I'll come to. Okay, so this is what a hyperbolic metric space is about. And now I'm repeating all that, saying that, okay, so now go back to that picture and you'll see that in order to fit it into R2, because of this theorem of Hilbert, you'll have to make limbs shorter and shorter. You can't fit it into this flat Euclidean space. So there is a fractal, there's a Cantor set for a tree. This is how fractals enter the picture. Third player in the game is symmetries. So symmetries, the mathematical structure coding symmetries are groups. Okay? Think of them as symmetries if you don't know what a group is. So what is a group? It's a collection of transformations. Yeah, those are, now you want from just to find a collection of transformations, you want to extract a geometry. Suppose it's just a discrete collection of transformations. Yeah, how do you extract a geometry from out of a collection of transformations? And here it is. So if you take a discrete collection of transformations called a group G, what is it given by? It's given by some transformations G1 through Gk, and it satisfies some relations, right? So for example, if you have say Z plus Z, yeah? So that means basically look at the group which corresponds to the tiling on this floor. Every point is going to be translated by an integer either to the right or to the left or to the top, yeah? Or right, left, top, bottom, yeah? That's the group Z plus Z sitting inside R cross R. Yeah? So what are you going to do now? So you say that it's generated by these two transformations. Point goes one step to the right. Its inverse goes one step to the left. One step forward goes up, and its inverse takes you one step back. These are your generators A and B, say, or G1 and G2. What is a relation? You go one step to the right, one top, one to the left, and one back, and you're back to where you started off with, right? So that means A, B, A inverse, B inverse. That's equal to 1. In an arbitrary group of transformations, this need not be equal to 1, right? So that's something that Z plus Z satisfies. That's an example. So A, B with one relation A, B, A inverse, B inverse, that's an example of a discrete group, a group which we know. This Z plus Z, the group of the styling. Okay? So, corresponding to any group, this is an indication. Actually, the styling, if you just look at these cracks, that's an example of the kind of graph that I'm talking about. So if you have an abstract group G given by finitely many generators G1 through Gk, finitely many relations, then you can construct a graph out of it, and a graph, if you put edge length 1, becomes a geometric space. What's the graph? Its vertex set has one vertex for every group element of the group. Two fellows are related by an edge if, to go from one point to the next point, you pick one of the generators. So the generating set you fix ahead of time. So if you can go from one point, one group element to another group element by multiplying by one of the generators, you join it by an edge. That means what? The entire collection of points in the group has now been converted into a graph. A graph is a geometric object. So from a discrete group of symmetries, out pops a geometric object. From a very algebraic abstract object, you suddenly have a geometric object popping out. Yeah? No, loops are possible. I mean, here in Z plus Z, you have loops. Yeah. So this is just a graph of a group. It's not a tree in general. So what is an example of a group where you do get a tree? You will only get it in this what is called the free group, where you have, so this is a free group on two generators, A and B, but there are no relations. So A and then B, then A inverse and B inverse is some point here. Okay, so B is here, A is here. They're completely unrelated. That's why it's called free. Okay, there are no relations between A and B. Then which means what? You can write down all words in formal words in A and B, A inverse and B inverse, so long as you don't write A and A inverse next to each other. If A is followed by A inverse, that cancels. So these are all formal reduced words. Yeah. So essentially what are you getting? You're getting collection of all words in 4 symbols: A, B, A inverse and B inverse. Yeah. This is used heavily in theoretical computer science, giving rise to regular languages and so on. So that's a different connection. I mean, these groups give rise to languages in finite state automata. I mean, the geodesics in this group are the language of geodesic words in this group is a language that is accepted by a finite state automaton. So it links up to theoretical computer science here. Anyway, so this is an example. So a free group on 2 generators is an example where the Cayley graph, this graph with these vertices and edges, is actually a tree where every vertex has valence 4. Okay. So what is a hyperbolic group then? A hyperbolic group is a finitely generated group. That means 1 to k, there are k generators, such that the Cayley graph with respect to that generating set, now it's a metric space, you can ask for triangles. That metric space is delta hyperbolic for some delta. Okay? So what are examples of groups that are hyperbolic? The free group is hyperbolic. What is a group that is not hyperbolic? Z plus Z is not hyperbolic. Okay? Z plus Z, you have these loops and you can have big fat triangles, and you can do this taxicab metric. Yeah? And then you get triangles which are fatter and fatter. Yeah? So Z plus Z actually reflects the geometry of flat Euclidean plane. The Cayley graph of the free group reflects the geometry of the tree. These are two different things. One is hyperbolic, the other is not. As soon as you have a tree, this starts accumulating towards a Cantor set at the boundary. Okay? So now what we have a notion of a hyperbolic group. And as soon as we have an absolute notion that we come up with in mathematics, A natural thing to ask is, what are natural subobjects? Which means you want to probe some huge space. What are its substructures? Yeah, so that you can understand the structure of the whole thing in terms of. So, for example, you want to understand a vector space in terms of its subspaces, a group in terms of its subgroups. Therefore, one would like to understand a hyperbolic group in terms of its hyperbolic subgroups. What is the so this is really where the problem starts. If you have a group, okay, so I'll give you one more example, and this is actually, hyperbolic geometry has been used by artists. So, so what is it? This is an example, I think Haridas mentioned in his little bit on hyperbolic geometry. This is an example of a triangle. So what do you do? This is a model called the Poincare disk model of the hyperbolic plane. What are the straight lines in this model? They are semicircles meeting the boundary circle at right angles. Okay? Those are the analogs of straight lines. And if you take 3 semicircles meeting each other, all of them perpendicular to the boundary, then inside, so this is an arc of a semicircle, this is actually a diameter. Diameter is an example of a semicircle because it hits the boundary at right angles. So you have this edge here, and this edge here. This angle is 90 degrees, but if you add these 2 angles up, you will get something that's less than 180 degrees. Yeah. So this is called a hyperbolic triangle. So if you take one of these triangles and then reflect them out inside this disk with angles pi by 2, this is pi by 2, this angle is pi by 4, that's pi by 4, and this angle is pi by 6, 30 degrees, 45 degrees, 90 degrees. This is a very symmetric hyperbolic triangle. Yeah? And you start reflecting this triangle, you're going to tile your unit disk by these triangles, smaller and smaller triangles as you go off to infinity. Okay? Okay, so this is a very bald picture. There's nothing very ornate, but then artists don't like this dry stuff, so they put some decorations. So this is a picture by Escher. Okay, the same thing. So Maurice Escher's pictures, many of them are actually examples of tilings of the hyperbolic plane of the unit disk. Okay, so here also what you have this inside, you have pieces of the geometry inside is hyperbolic, and you have what looks like a very nice smooth boundary, one dimensional, but it's actually a fractal whose fractal dimension is integral. See, basically when you go out, you start seeing the structure that it's extremely, the tiles are becoming very, very small. So if you try doing calculus, you'll fail from inside when you go to the boundary. Yeah? There is a way you can do that stuff intrinsically on the boundary. So it's an accident that the fractal dimension is integral here. Yeah? Okay, good. So this is another example. So here we have here's the problem that we pose. So try to understand a hyperbolic group in terms of subgroups. Yeah? What is the interaction between subgroups which intrinsically have hyperbolic geometry and the ambient space? Yeah? So for example, a saddle is something that's negatively curved. What if the ambient space is also negatively curved? How would its geometry interact with the geometry of the ambient space? This is extrinsic curvature in the classical Gaussian notion. So here's the abstraction. Suppose you have a hyperbolic group G and you have a subgroup H. So subgroup H has its own generating set, finite. With respect to that generating set, that also has a hyperbolic geometry. This is your hypothesis that's given to you. So it's a hyperbolic subgroup of a hyperbolic group. Then the Cayley graphs, as a subgroup, all the elements are elements of the big group. So there's an inclusion of the subgroup into the big group. You assume that the generating set for G contains the generating set for H. Yeah? And you have an inclusion of the Cayley graphs, right? So the geometric objects include, right? The nicest possible thing. Point includes as itself in a larger space of points. What happens at infinity? Yeah? I have mentioned before that these hyperbolic groups have some fractal boundary. Question that you're asking is, how does the fractal boundary of the sub-object interact with the fractal boundary of the big object? Yeah. Since it's fractal, you can't hope for any calculus, any smooth stuff to go through. Can you even expect continuity? Or I mean, is some tearing necessary? Okay. Here's how you make that question precise. So basically you want to ask for, okay, you have a sub-object of an object. What happens asymptotically at infinity? Does the boundary map continuously to the boundary? That's what you're asking. Does the inclusion of Cayley graphs extend to a continuous map between the fractal boundaries? So this question was posed somewhat, in this generality it was posed in 97 or 96, but in this generality the answer is no. The counterexample was found relatively recently. However, there is an analogous question, and now we are coming to the tail end. So, okay, so you have so I'll give you an example of a continuous map, which is very nice. So you take the Cantor set. Yeah? So it's 0, 1. Yeah? So assume that 0 and 1 are identified to a circle. Yeah? So you have this one circle there. And then what do? You start removing the middle 1/3. Yeah? After removing this middle 1/3, you have this Cantor set arranged in a along a circle in a circular order. What will happen if you take the boundary points of the Cantor set? I mean, so you've thrown out, say, 1/3, 2/3. Yeah? Now, after throwing out, you take 1/3 and you take the point 2/3. There's nothing in between. Paste those 2 points together. Pasting is a continuous operation. Cutting is not. Tearing apart is a discontinuous operation. Pasting 2 things together is a continuous. Yeah? I mean, 2 points can move continuously and then collide. Yeah, but if 2 points are already the same, 1 point breaking suddenly into 2 is a sudden operation. 2 points come closer and closer together at uniform speed, and finally they just merge at a point. Yeah. So that's a continuous operation. So if you take 1/3, 2/3 and you glue all the endpoints together, what will you get? You get back your circle. So if you have your Cantor set, it has its pairs of endpoints. Those fellows are pasted together, so you can recover from the Cantor set by pasting points together in a circular order. So from the Cantor set, there's a very formal way of looking at it. What is the Cantor set? It is ternary expansions with 0 and 2. So you base 3 expansion, you write a number as 0.0220, etc. What you mean is that 0 by 3 plus 2 by 3 square plus 2 by 3 cubed, etc. Now formally divide it by 2 and think of that as a binary expansion. Yeah? Then what you're getting is exactly this pasting operation. Yeah? And that gives you maps from the Cantor set to the interval, closed interval. Yeah? So the endpoints getting pasted together. So you take the middle 1/3 and throw it away. Just imagine 2 intervals, right? You took 0, 1, take the middle fellow and throw it away. Now you have 2 intervals. Now I paste these 2 together. What do you have? You have your your original interval back, right? So from the Cantor set to the circle, there's a continuous map. Yeah? So that's the question that one is asking in general. Okay, fine, you might not have an injective map because the geometry, actually, if the map is not injective, it says that the geometry of the subgroup is very distorted in the big group. But there's still something that you can manage at infinity. Yeah? So that's the question, but in this generality, its answer is not known. It connects up to something, which I'll come to. But an analogous question and a classical question arises in the case where you have a group, say that group of symmetries that we just talked about. Yeah? This Escher's group of symmetries of the hyperbolic triangle. So there's some subgroup which acts now not on the 2-dimensional plane but on 3-dimensional space. This 2-dimensional guy has its boundary a circle. The 3-dimensional space has boundary a sphere. When you have this subgroup acting on hyperbolic 3 space, do you get a map from the circle to the sphere? In the Cantor set to the circle, or Cantor set to the interval, it's a 0-dimensional space mapping continuously onto a 1-dimensional plane. We are asking for that same problem in 1 dimension higher. Not we, actually Thurston asked this question. Okay, so is there a map? So in the case, so if you have a group acting on 3-dimensional space, is there a map from the boundary of the group, thought of as a hyperbolic group, to the boundary of this classical space, which is the 2-sphere? That was the question. Yeah? So is there an interaction between the fractal boundaries in a very specific case where on the right side, the target, the boundary is a sphere, and the domain, the boundary is a circle? So what is H3? I've just formally defined this. It's just the upper half space x, y, z with z greater than 0, equipped with a metric. Take the Euclidean metric dx square plus dy square plus dz square, just divide by z square. Yeah. The boundary of this space, the space at infinity, is the complex plane union infinity. So now we have at least the features of that picture I had shown you long back. This complex plane is this blue plane on the board, infinity is out there, and this three-dimensional room is an example of hyperbolic free space, now equipped with this metric. Now, as soon as you have a group of symmetries acting on a nice geometric space, immediate geometer's instinct is to remove away all superfluous symmetries by passing to a quotient of the ambient space by the group of symmetries. What do I mean by that? Take an illustration, take the Euclidean plane, take z plus z acting by translating tiles. What is the quotient of the Euclidean plane by this group of symmetries? What is it? So basically every integer gets translated by 1 to the right or 1 to the left, which means what? The square tile translated by integers covers your entire plane. But the bottom edge of this tile gets identified with the top edge of the tile. The left edge of the tile gets identified with the right edge of the tile, which means what? You take the square, bottom identified to top, left identified to the right, and you get this nice round torus as a result. That's an example of what one means by saying take z plus z acting on R2, pass to the quotient, you get a torus. Okay? So this is really what it means. Even simpler, in one dimensions, if you had just the real line and you have the integers acting on it by translation, then just the interval 0, 1 with endpoints identified is your quotient space. What is that? That's a circle. Now, there are more and more exotic examples. You can take the two-dimensional disk, and you take one example was that triangle with angles pi by 2, pi by 4, pi by 3, and you had a tiling. Yeah? Or you can do an octagonal tiling, and then when you identify again opposite sides, this side, this is A, B, and then this is A inverse and B inverse. So it's this side and this, the alternate sides are identified. You get this genus 2 surface. You get two tori tubed together in the middle. Yeah? So that's another example of the hyperbolic plane being quotiented by a group of symmetries to get a very nice geometric object, not as simple as a torus, but still manageable. And here's the, so now equipped with this, what we understand, now that we understand what quotienting means, we return to the three-dimensional problem, and we now have a discrete group. Remember that a discrete group comes equipped with some finite generating set, a Cayley graph, hence a boundary. Yeah? In the context that we are going to be interested, these groups are going to be intrinsically hyperbolic, so they'll have a boundary which is also a fractal boundary. Yeah? And the group of isometries of this three-dimensional space is the same as the group of fractional linear transformations or Mobius transformations. Z goes to AZ plus B by CZ plus D. Complex automorphisms of the Riemann sphere. Yeah? Just AZ plus B by CZ plus D. Yeah? This is called the Mobius group. It has various incarnations in terms of the complex analytic angle. You call it the Mobius group. If you think of it as geometric objects acting on the three-dimensional hyperbolic space, that's the isometry group of hyperbolic free space. And therefore, as soon as you have a discrete group acting on hyperbolic free space, you can pass to the quotient. And this group of that discrete group actually appears inside the quotient manifold as the number of ways you can wrap loops around it. Yeah. So if you have this Z acting on R, you pass down to the quotient circle. Where is the Z? That Z encodes how many ways, the winding number around the circle. That's where your Z sits. Okay. So this discrete group acting, it's got a name. When you pass to the quotient, it's called the fundamental group of the space. It becomes the topological invariant of the space that you are considering. Yeah. So now we are linking up with the other player in the game of here, it's the topology. So this group, discrete group G, now appears in a new incarnation. It was being thought of as a group acting on hyperbolic free space as a group of isometries. Now after passing to the quotient, it appears as the fundamental group, the number of ways you can wind strings around in the quotient manifold. So now you have various different things. So there's sort of too many ways of looking at it. Probably, yeah. There's this Lie group's way of looking at it. 2 cross 2 matrices with determinant 1 with complex numbers A, B, C, D. Or you can think of it as acting on the two-dimensional complex plane union infinity as Mobius transformations, Z goes to AZ plus B by CZ plus D. Or you can think of it as a discrete group of isometries of three-dimensional hyperbolic space, or you can think of it as a fundamental group of the quotient manifold. Yeah? So there are zillions of ways you can think about this. Question is, seems all very disparate amount of information. How do you put all of it together? Yeah? And this was really what was conjectured by Thurston, and we'll try to get at a precise statement as we go on. So the sphere appears as the boundary of hyperbolic 3 space, and Mobius is this, I've just written down the formula for an abstract Mobius transformation, A, B, C, D complex numbers. Here's the theorem that ties it all together. There is, I'll state it in an imprecise form. There is an exact dictionary between so you have this group G now acting by complex analytic automorphisms on the Riemann sphere. If it's some finite amount of space and you have an infinite fellow acting on it, it'll mix various things up, right? So if you have this finite square, let's say, and you have some infinite group, yeah, which means an infinite number of symmetries inside it, yeah, then some point is going to come very close to itself infinitely many times. So on a compact object like the Riemann sphere, something that is bounded, there's going to be a lot of chaotic stuff going on. Yeah? That's where the chaos of the title comes in. Yeah? Inside the three-dimensional space, everything is nice. The action is nice, you can pass to a quotient. There is no chaos in the three-dimensional picture. So what the theorem says is that the dynamics, which is more precisely the chaotic dynamics of the group on the Riemann sphere, here's where the fractal is hidden, and the geometry of the three-dimensional quotient of hyperbolic 3 space by this discrete group, that's where the hyperbolic geometry is located. There's an exact dictionary between one to the other. These two ways of looking at it encode the exact same amount of information, which means what? From hyperbolic geometry, you can go to complex dynamics. From complex dynamics, in 2 dimensions, you can recover hyperbolic geometry. So the two are, so setting up this dictionary was a conjectured picture. So we'll try to make this. This is an exact dictionary. What does it really mean? We'll make that a little more precise and then stop. Okay? So how does the chaotic dynamics occur? You look at an infinite group acting on the Riemann sphere, then a point, say take the North Pole, you act on it by an infinite group, it's going to accumulate on some collection of points. That collection of accumulation points has a name, it's called the limit set. Yeah? So this limit set is the set of accumulation points in the Riemann sphere of the orbit of a point in hyperbolic 3 space. Hyperbolic 3 space is that three-dimensional ball inside the sphere. So you take maybe the origin of the ball, act on it by the discrete group, see at what points at infinity it accumulates on. So for the 2, 4, 6 group, that actually preserves this equatorial plane. The limit set is exactly this round circle. For the genus 2 surface, also the limit set is this round circle. So the intrinsic boundary, the round circle, sits in the extrinsic object in the sphere just as an equatorial thing. But you can go further than that. So the intrinsic boundary just embeds as a round circle in S2. So that's the nicest possible inclusion of the intrinsic boundary in the extrinsic boundary. You can start deforming these examples. The circle becomes, as soon as you start deforming, the circle becomes a fractal. This is a fact of life, okay? What happens if you allow this deformation to go off to infinity? This is what Thurston had asked. So the limit set, you should think of the limit set as the place where chaotic dynamics of the group G is localized. It's the locus of chaotic dynamics. And so the question becomes, the more precise version of this question becomes, you have this inclusion of the Cayley graph from of the inclusion of the Cayley graph to hyperbolic 3 space, sending any point of G to where it maps a specific point, say the base point. So basically sending a group element, the group to the orbit. And the question that is being asked is that does I extend to a continuous map between the circle boundary of G? So think of G as one of these, either the fundamental group of the genus 2 surface or this reflection in pi by 2, pi by 4, pi by 3 triangle. And so the question that Thurston asked was, is there such a continuous map? And this continuous map, the first non-trivial example for this was due to Cannon and Thurston, was an example of a sphere filling curve. Just as you have a Cantor set filling out an interval, Thurston and Jim Cannon came up with an example where a circle fills out a sphere by pasting various things. So that's why it's called a Cannon-Thurston map. It's the example of such an extension. 0 to 1 is Cantor set to circle, 1 to 2 is a Cannon-Thurston. That's what it is. Okay. And Thurston asked essentially whether this example is a very general phenomenon, whether it exists for all groups G acting on hyperbolic 3 space. And here's the answer. Cannon-Thurston maps exist in the fullest possible generality for dimension. So if the ambient space is the 3-dimensional hyperbolic space, boundary is the Riemann sphere, then it always exists. Okay? So there's a happy ending to the story in this classical situation, though in general the answer is no. Okay? And what does this give you? Why is it important? Basically, it says that the locus of chaotic dynamics is not terrible, it can be tamed. Yeah? Tamed in the sense that you can parameterize it by, locally parameterize it by an interval. Something that is parameterizable by an interval is what's called a piano continuum. Yeah? So if it's parameterized, then you can still work with it. You can move from one point to a point nearby along a path. So such spaces are called locally connected. So that immediately follows from this. Okay? There's something that's a little more. The quotient object that we had by quotienting a 3-dimensional space by a surface group. See, if you take the 2-dimensional space, just this R2, and you quotient out by this Z acting on it, you'll get an infinite annulus, right? If you take a real line quotient out by Z, you're going to get a circle. If you quotient out the 2-dimensional plane by a Z, you're going to get an annulus. Non-compact object, infinitely extended in 2 directions. Similar thing happens in one higher dimension. If you have a surface group acting on 3-dimensional hyperbolic space, you get something like a surface with infinite extension on both sides. So if you have infinite extension on both sides, Thurston proved that there is some topological information appearing at infinity. These guys are called ending laminations, and this was another of Thurston's major conjectures. Essentially, it says that you have a topology at infinity of the quotient manifold that determines the geometry of the manifold completely. Topology at infinity determines geometry. The Cannon-Thurston map actually tells you the asymptotic topology. So there's a theorem which says that the asymptotic topology in the previous theorem can be captured from this map. So essentially, it's the information of the boundary points of the Cantor set in the previous example. So this asymptotic topology is determined by the Cannon-Thurston map. Put all of this together, and you have a precise version of the statement that chaotic dynamics on the boundary determines and is determined by the geometry of it. Okay. Yeah.
There is let's say we have a group, hyperbolic group, and there is a subgroup. So you know that if we apply subgroup, we have a structure.
A subgroup, so for example, in this particular example, the subgroup is your 2, 4, 6 triangle group. Yeah, its boundary is a circle. Yeah, the boundary of the 3-dimensional hyperbolic space is a sphere. Question 1 is asking is that you have this subgroup acting on this 3-dimensional space instead of 2-dimensional space. Does the circle sit nicely inside the sphere? Always. That's really the question. And in the simplest case, it's just a round circle. You start moving it a little bit, it starts getting distorted. If you distort it a little bit, it becomes a fractal circle. What if that distortion goes off to infinity? And here, in that case, what Cannon-Thurston proved and what I had proven, what I generalized to in the most general setup, is that you get an example, you do get a continuous map from the circle to the sphere. It does not sit even topologically inside the sphere. It can fill up the whole sphere, for instance. From the circle onto the sphere is a continuous map. So from this 1-dimensional interval onto this 2-dimensional square, there's a map which you can get by just pasting points together. And you fill up the whole 2-dimensional square. That's an example of the map. Yeah.
3 groups that you made.
Yeah.
What exactly is the topology at the boundary?
That's a Cantor set. That's exactly what a Cantor set is. It's the same thing as, the trees that we had drawn initially, their boundary is a Cantor set. The free group, the boundary is a Cantor set. What is an open set in the Cantor set? Yeah, sure. Okay, that's a nice question. A good question. Let's go back to that picture. You can start seeing the how are you going to see open sets on the boundary sphere if you are in hyperbolic free space and your point is O, right? So here you have this visual sphere at infinity. Yeah. So what is going to be a small open set? Something that subtends a small solid angle, open solid angle at my eye, right? So it's just a small patch, and you see it from your eye. It's subtend a small open angle. That's what an open set is, correct? On the sphere, viewed from O, right? Now let's go back to the Cantor set. Just a moment. So here, on this circle, what is an open set? Take this point, take a geodesic going off like this, take another geodesic going off like this, or the entire stuff between two geodesic rays. That's an example of an open set. Now you start making those geodesics come closer and closer together. Okay? Same thing, go down to this picture. What is a geodesic? Some path from here that goes all the way to infinity, for instance here. And you can take this B and then go off to infinity. All the points between this point and this point, meaning all these points in the fractal. That's an example of an open set. That's right. So that's what I'm saying. So if you start off from here, what is the in-betweenness is going to be, here it's given in terms of a planar embedding. How are you going to say whether an open set is small or not? You have your base point E, right? This is actually a very nice question. So you take a geodesic going all the way, say we want a neighborhood of this point. Just a power infinity. What are going to be the, look at all words whose initial segment is a power n. N is 10,000. And then it starts doing whatever it likes. A power 10,000, then B inverse, A to the minus 37, B to the 42, etc., etc. You allow all things, only restriction is that the first segment of length 10,000 is just all A's. Then the collection of all those rays at infinity is a neighborhood of A power infinity. You should think of it as a cone. You go along many steps and then you allow everything to flare out from there. So the initial segment you fix. Yeah? And the longer the initial segment you fix, the smaller is going to be your angle. If you fix all infinity, you're going to get a single point, right? So what is the sequence of neighborhoods of A power infinity? All words which start with A power 10,000, A power 100,000, A power 10 power n, where n goes off to infinity. You have a sequence of neighborhoods. What is a neighborhood? Neighborhood has to be smaller and smaller, right? So A power 10,000 means, so for example, you think of it in Euclidean space. Angle of theta equal to 1 by 10 radians. These are small open sets which contain, union of our two open sets is always an open set. Take any open set containing A, take any open set containing B, take the union of that, that's good.
Second thing is, after you map all these fractal structures onto the spherical surface.
Yes.
So now that these are simply connected parts along the surface of sphere, can you write properties like once you map line onto a spherical surface using the Darboux-like transformation mapping?
No, these are fractal maps. Okay, so they are just continuous. There's no differentiability properties. Okay, so it's a map onto a sphere. It's a fractal of dimension 2. That's why you can't do any calculus there. You can't differentiate. You can't do anything. Lines. See, what you're taking is just a small arc in a line, but it's going to go all over the place on the sphere, right? It's going to fill up a definite amount of space. So you can't do any calculus. You have no hope of any calculus. The best you can hope for is a continuous map. From that continuous map, you can recover some information. So if you want to do calculus on the boundary, bad luck. What you have to do is go through from that, recover some information, go back to the three-dimensional space where everything is nice, where you can do calculus. You can't do calculus intrinsically on the sphere. Yeah? So that's why all this dictionary is required. You can't do it on the sphere itself. Nothing is smooth. Yeah? In fact, when you take that circle and you twist it a little bit, there's a theorem which says that you distort that circle a little bit, the smallest amount that you can, you're going to get a fractal. The circle is I mean, you can start off with the round circle limit set of the triangle group, for instance. But well, maybe the genus 2 surface group. Then you can twist it a little bit, it becomes a fractal. Fractal dimension becomes more than 1, but less than 2. You start distorting it more and more, more and more. In the limit, you're going to hit 2. Because the ambient space is 2-dimensional. And in the 2-dimensional case, you have the maximum you can hope for is this continuous map. Question was whether you at least have this much. I mean, whether the maximum you can hope for is there. Yeah? Answer is yes. Yeah? From that, you can recover the topology of the manifold at infinity. From that, you can recover the geometry of the manifold.